So the first lecture is given by Chris Leininger, and he will talk about the exact title.
Teichmüller geometry and pseudo-Anosov.
Thank you, Chris.
Okay, thanks both Iran, Pierre, for organizing this and for inviting me. So this is, so I'm supposed to talk for an hour and a half, and maybe we'll take a break in the middle if I see people are going like this. So this is a summer school, so some sort of mini course, and I wasn't really sure. Looks like pretty varied audience, so hopefully this is the right level. It will be, I know a lot of you know all of what I'm going to say. It's not for you. Right, so let's just get started. I'll mostly be assuming basics from sort of complex analysis and maybe a little geometry and some geometric topology. So what's the setting? So we have X will be a Riemann surface. So I'll just write RS. So that's a one-dimensional complex manifold. That means it's a two-dimensional real manifold that has charts to the complex plane, and the transition functions are holomorphic maps. And I'll assume that it's closed with genus G at least 2. So what does that mean? That means it looks something like this. So here's an example of a genus 3 surface. The Riemann surface homeomorphic to topological surface. It's closed and genus at least 2. Okay, so let me write the universal cover of X. So this is simply connected covering space. The complex structure on X lifts to a complex structure on X tilde, so that this map P is a holomorphic map. So X tilde admits a complex structure so that P is holomorphic. Right, so how does that work? Well, you just take your charts on X. This is a local homeomorphism in particular, so you can compose with that local homeomorphism that gives you charts on X tilde, and the transition functions are the same as the transition functions on X. Okay, so what else? So there's some algebraic topology already creeping in here. There's an action of the fundamental group of X on the universal cover. So basic covering space theory says that X is the quotient tilde by a group, and in fact that group is isomorphic to the group of homotopy classes of base loops. Okay, so that's pi 1 of X. Now let me just write the action. So if gamma is in here and X is in here, I'll just write this as a function, gamma of X. Okay? Great. So there's going to be lots of, because this is a course, there's going to be lots of exercises as we go. Some sketches of proofs, outlines of proofs. Some of the proofs will be the exercises. Okay, so let's, I want to bring in hyperbolic geometry. So let me remind you of the uniformization theorem. So this is actually a corollary of the uniformization theorem. So it says that, so the uniformization theorem says that any simply connected Riemann surface, so X tilde is such a thing, is a holomorphic diffeomorphism to either the Riemann sphere, the complex plane, or the disk or upper half plane. I'll use the upper half plane instead of the disk. So the universal cover is non-compact, which means it can't be the Riemann sphere. And basically what I'm going to describe will explain why it can't be the complex plane, because the genus is at least 2. And so what that says is that there exists a holomorphic diffeomorphism D from x tilde to the upper half plane. So these are points in the complex plane so that the imaginary part of z is bigger than 0. Okay. So, right. Now, this action of pi1 of x on x tilde preserves the complex structure because it's obtained by pulling back the complex structure on x. So gamma as a function from x tilde to x tilde is holomorphic. Which means that if I conjugate this holomorphic map by D, so I can write D inverse gamma D, so for all gamma in pi1 of x, this gives me a holomorphic map, right? It's a composition of 3 holomorphic maps. So this is a holomorphic map. And let me call this rho of gamma. So for every element of pi1, I get a holomorphic map from H to H. I'm just conjugating this holomorphic map to one on H. And in fact, this conjugates the action of pi1 of x to an action on H. So we get rho is a homomorphism from pi1 of x into the group of conformal or holomorphic automorphisms of H. So these are maps T from H to H such that T is holomorphic. Okay, so well, what is the group of holomorphic automorphisms of the upper half plane? Well, they're the linear fractional transformations. So this follows from the Schwarz lemma. Maybe I'll just write it here. I'll leave it as an exercise. So this is the set of maps T from H to H. That T looks like AZ plus B over CZ plus D, where AD minus BC is real, but in fact, and positive, we can take it to be 1. Okay, so are real, thank you. Yeah, A, B, C, D are real numbers. Okay, so so this looks familiar, right? These are 4 numbers. They're arranged in the square. The determinant is 1. So not surprising, there's a homomorphism from SL2R. So the group of 2 by 2 real matrices with determinant 1, there's a homomorphism from here to here that just sends the matrix ABCD to this linear fractional transformation. And the kernel, well, what's the identity? The identity is when ABCD is either the identity or minus the identity. So this is, the kernel of this is plus or minus the identity. So actually, I'm going to just think of this group as the quotient of this group, which is often called PSL2R. Okay? All right. Okay, any questions? So far, so good. Just complex analysis. Well, if I take the quotient of x tilde by the action of pi1 of x, I get x. If I take the quotient of h by this other action of pi1 of x, namely rho of pi1 of x, so let's say rho of pi 1 of x. Let's call that G. This is now a subgroup of this automorphism group, PSL2R. And if I take H modulo this, this action, well, the holomorphic map, D, from x tilde to H, descends to a holomorphic map to the quotient. And let me just identify X with this quotient. OK, so our Riemann surface looks like the quotient of the upper half plane by a subgroup of PSL2R acting by these holomorphic automorphisms. Make sense? OK. All right, well, let's write the covering map as P. And so now let's look a little closer at this group. So this group preserves a metric on the upper half plane, which is the hyperbolic metric. So let me define, in case you haven't seen it before, the hyperbolic metric on H. So this is a conformal metric. It's a Riemannian conformal metric. So I'm just going to tell you what the inner product is, or the norm is, on the tangent space at every point. And it's just going to be the Euclidean inner product, the Euclidean norm, divided by the imaginary part of Z. OK, so what does this mean? This means if I have a pair of points, and I have a path between those points, I can, so here's Z and here's W. First, I can define the length of this path. So the hyperbolic length of this path to be, let me write this maybe D H. So if I were to compute the length of this path, I would integrate, let's say gamma is parameterized. I would integrate from 0 to 1 the length of the tangent vector dt. Okay, that's the Euclidean length. But if I want to compute hyperbolic length, instead of taking the Euclidean norm of the tangent vector, I should take the hyperbolic norm. So this defines the length of a path, okay? And then the distance between 2 points, so the hyperbolic distance between x and, so Z and W, is the nth over all such gamma like that, of gamma. So this is the usual way you take a Riemannian metric and you turn it into a metric distance function. OK, questions? I realized I should have started on the top board. I'm going to cover everything up. Or maybe I'll just, should I use this top board? Or should I? Pause. All right, I'm going to cover it up. This one doesn't move. OK, let's just keep going. 3 boards is enough, I think. OK, so let me point out some properties of the hyperbolic metric, and in the form of exercises. So maybe proposition. Let's see. So PSL2R is the group of orientation preserving isometries of this metric. These are orientation preserving isometries. So that's 1. Maybe 2 is that geodesics. So geodesics are length minimizing paths between pairs of points. Geodesics are arcs of circles and lines orthogonal to the real axis. So here we have the real axis sitting inside of the complex plane, which sort of sits at infinity of H, so the boundary. So for example, the line orthogonal to the real axis, any arc of that is supposed to be a geodesic. Or I could take any circle orthogonal to the real axis, any pair of points on there, and the distance is the length of that path. So this is a geodesic. Okay? So I'm not going to, maybe the proof is exercise. Let's say exercise with hints. So maybe for the first one, what's the hint? Well, you just need to show that the length of every curve is preserved under an element of PSL2R. So if P is in PSL2R, you need to show first that the length of any curve is equal to its length if you apply this transformation. And this you can show using the chain rule. So this tells you at least that this is a subgroup of the orientation-preserving isometry group. Let me give you a hint for part 2. So PSL2R acts transitively. So that means any point can be taken to any point in H by an element of PSL2R. That's pretty straightforward. And isotropically. And that means that the stabilizer of a point is as big as it can be. Namely, the stabilizer of a point is isomorphic to the group of rotations. Okay. Okay, so it acts transitively and isotropically. Sorry, this is still part 1. This is still part of 1. Part 2 is that this also acts transitively on lines and circles orthogonal to R. Okay, so this set of things that are supposed to be geodesics, PSL2R acts transitively on those things, the bi-infinite geodesics. And then the last part of maybe the hint for part 2 is if I have 2 points, they live on, you can find one of these lines or circles that it lives on, and then you can apply the first part to give, to find an element of PSL2R that takes that circle, if it's a circle, to, let's say, the imaginary axis. And now you just need to show that 2 points on the imaginary axis, the segment between them is a geodesic. And for that, look at the projection from all of H to the imaginary axis. That just sends xy, x plus iy, to iy. Okay? And show that the length of the curve under this projection is shortened, unless it already lives in the axis, in which case it's equal. Okay, so those are hints. Maybe you already know this, I'm not sure. What else? So, well, once we have, so let me say a little bit more about these isometries. So another proposition is, so once you have this, then the group of orientation-preserving isometries is the group of holomorphic automorphisms. How do they act? So what are the elements? What's the classification? So the classification of isometries. So how do I want to say this? So given T, PSL2R, let's say not the identity, then one of the following happens. Then either, 1, T fixes a point in H and is conjugate to, let's call it T naught of Z, just looks like cosine theta Z plus I minus sine theta over sine theta z plus cosine theta. So this T naught is in the stabilizer of I, and it's just acting by rotations by angle 2 theta. Okay. So if I have a fixed point, I can conjugate that fixed point to I. If I can find some element of PSL2R that acts transitively that moves it to I. If I conjugate by that, this element looks like a rotation about I, which means that this thing that fixes a point in H looks like a rotation around that point. That's one possibility. Another possibility is that T acts by translation on a geodesic. So it leaves invariant some geodesic, so there's some line or circle that's invariant under this transformation. Okay, the geodesic is isometrically embedded copy of R, and we're acting by translation on that geodesic. So that's another possibility. T acts by translation on a geodesic. And this case is conjugate to, let me call it T naught of z now, that looks like lambda z plus 0 over 0z plus lambda inverse, which is also lambda squared. So it's just a dilation of the upper half plane. So this obviously leaves invariant an axis, namely the imaginary axis. Okay? It's acting by translation. The translation length is 2 log lambda. Okay? And then the last possibility, so this, or the last possibility is that T fixes a unique point, not in H, but on the boundary of H. And the boundary of H is R hat. So it's the real line union the point at infinity. So if you want to think about C as sitting, the complex plane as sitting inside of CP1 of the Riemann sphere, then the closure of R inside of there is just adding infinity. And that's the circle boundary of the disk, which is the upper half plane. Okay, so these things are called respectively elliptic, hyperbolic, and parabolic. I'll finish this. Let me write called elliptic. These are called hyperbolic. And these are called parabolic. So in this case, T is conjugate to something that looks like T naught of z, z plus 1. Okay, so in the upper half plane, it's translating to the right. And alternatively, you can describe this point at infinity as, so in this case, T moves some sequence of points a smaller and smaller amount. Okay? That's clear for this transformation. It sends points that are higher and higher in the upper half plane. They're translated by 1, but in this funny metric, the hyperbolic metric, those points get closer and closer together. So this is the same in this case as saying that there exists xn, or let's say zn, in H, so that the distance between zn and tzn goes to 0. Okay? And these points that have this property limit on R hat to the unique fixed point. Okay. All right, so there's the classification of isometries. The proof is another exercise. What's the hint? The hint is linear algebra, or Brouwer fixed point theorem. There are various ways that you can try to prove this. They're mostly computations. Okay? All right. So Right. So, great. So now we have all this information about this group of holomorphic automorphisms. It's actually the group of isometries of the hyperbolic plane. Which means that if you want to think about Riemann surfaces as complex one manifolds, that's great. But you can also think about them as hyperbolic surfaces. So what do I mean? So let me note. So let's go back to our action pi1 of x on H. So that was G, rho of pi1 of x. That's G, subgroup of PSL2R. And x, remember, was H mod. I can't remember to write it on the other side. So it's H mod the group G acting. So this is acting by isometries. Now, not only is it acting by holomorphic automorphisms, it's acting by isometries, which means that we can define a metric on a Riemannian metric on X so that P from the universal cover to X is a local isometry. So not just a holomorphic map, now it actually is a local isometry. And how does it work? So here's our surface. It's the quotient of the upper half plane. How do I define the metric here? It's the same way as before. I take a pair of points and I connect them by a path. Now I need to measure the length of a path. Well, I can lift the paths, because this is the universal cover. I can lift the path and measure its length there. And then any two lifts differ by an element of the covering group. The covering group's acting by isometry, so the length doesn't change. Okay? All right. So my Riemann surface has a metric. So X has a metric. So let's say define a metric. Let's call it d sub x. So d sub x is locally isometric to the hyperbolic plane with its hyperbolic metric. Now what's great is that we can go the other way. If I have a surface with it's locally isometric to the hyperbolic plane, I can lift that metric to the hyperbolic plane. Or sorry, lift that metric to the universal cover and prove that that universal cover is globally isometric to the hyperbolic plane. Okay? So conversely, if we have a surface, if X is just a surface, so a topological surface with a metric locally isometric to the hyperbolic plane, then this is sometimes called the Killing-Hopf theorem. In this case, you can prove it maybe a little more directly. But what does it say? It says, the Killing-Hopf theorem says that then the universal cover of X isometric to H. Said differently, there exists a locally isometric covering of X by the upper half plane with the hyperbolic metric. Okay? So I can think about starting with the Riemann surface and then building this metric that makes it locally isometric to the hyperbolic plane. Or I could start with a metric that makes it locally isometric to the hyperbolic plane. And then its universal cover is H. The covering group's acting by isometries. So again, this looks like H mod G, where G is a subgroup of PSL2R. But then, because PSL2R is acting by holomorphic automorphisms, that means that X is also equipped with a Riemann surface structure. So you can go back and forth between hyperbolic structures, or hyperbolic surfaces, and Riemann surfaces. And what we'll be interested in Teichmuller space is when two such things are equivalent. And so maybe an easy proposition. Suppose x and y genus G Riemann surfaces f from x to y, an orientation preserving, let's say, homeomorphism. Then this homeomorphism is holomorphic if and only if it's an isometry. Then f is holomorphic if and only if it is an isometry. And whenever I talk about a Riemann surface and a metric, I mean the hyperbolic metric, the one locally isometric to the hyperbolic plane. OK, so what's the proof? Well, we take the covering of x by h and y by h. We have the map f, and we can lift f to the universal cover. Now f is an orientation preserving homeomorphism from h to h. And we know that it's a holomorphic map if and only if it's an isometry. So this is holomorphic if and only if it's an isometry with respect to the hyperbolic metric, which means the same is true of f, because that's the local property. OK? All right. So now we can freely sort of move back and forth between Riemann surfaces and hyperbolic surfaces. And we'll do that whenever it's convenient. Let me just, since we have this up here, let me describe one more useful thing that you can do with this hyperbolic metric. So proposition. So again, x will be Riemann surface, genus G at least 2. And let's let gamma from the circle into x be a non-null homotopic curve, closed curve. OK, so well, the free homotopy class of this curve, so that is just arbitrary homotopies, no base point or anything. The free homotopy class of any curve corresponds to a conjugacy class in the fundamental group. I can pick a base point on there. And as I do free homotopies, I'm essentially changing the base point. Okay? Ultimately, that corresponds to conjugacy. So let's also let gamma naught in pi 1 of x be a loop representing the conjugacy class determined by gamma. Okay? So a closed curve determines the conjugacy class. Let me pick a representative of that conjugacy class. Then, gamma is homotopic to a closed geodesic. Call it gamma star. So that's a locally isometric embedding or immersion of the circle up to scaling. Sorry, maybe I should think about this as a circle of varying radius. OK? Or think about it as a maybe some parameterization of locally isometric embedding, immersion. OK, so gamma is homotopic to a closed geodesic. The image, so remember rho was our homomorphism from pi 1 of x to g elements of PSL2R. So this element of pi 1 acting on the universal cover is a hyperbolic isometry. And 3, the length of this geodesic representative of the homotopy class is equal to 2 arc cosh of the absolute value of the trace of rho of gamma naught over 2. Okay, so rho of gamma naught is an element of PSL2R, which remember is the image of SL2R under this homomorphism. So I can pick a representative matrix and take its trace. That's well defined up to sign, so I take the absolute value and I get a well-defined number. And we're saying that the length of this geodesic representative is given by this nice formula. Okay. So the point though, is just to relate somehow the geometry of this metric down on x, right? X is now this surface that has this locally hyperbolic metric. That geometry is related very intimately with this homomorphism rho. Okay? All right. So let's take 5 more minutes. I want to take advantage of this this way of viewing Riemann surfaces as hyperbolic surfaces to give you a way of constructing hyperbolic surfaces or Riemann surfaces. So, so far, I haven't given you a single example of a Riemann surface. That's no good. So using this, what's that? Yeah, okay, sorry. Genus, closed Riemann surface. Thank you, Greg. So, okay, I did mention CP1, so genus at least 2. All right, so in fact, using hyperbolic geometry, you can construct every Riemann surface in a very concrete way. So let's do this in 5 minutes, and then we'll take a short break, because I'm roasting. It's not because I'm overweight. Okay. Using hyperbolic geometry, let's construct all Riemann surfaces of genus G, at least 2. Well, I mean, construct them up to holomorphic diffeomorphism, or up to what I'm really thinking is up to isometry. Okay? So let's do it in steps. Step 1. Step 1 is proposition right-angled hexagons in the hyperbolic plane. So let's draw a picture. What's a right-angled hexagon? It's a hexagon where all the angles are right. So what do they look like? Okay. So here's a right-angled hexagon. There are side lengths A, B, C, and opposite sides A, B, and C. So right-angled hexagons in H are determined up to isometry by alternating side lengths. Well, not only, I mean, in fact, if you just want to construct examples, you just need to know that there are some. Okay, and I just drew one. But in fact, you can parameterize all the right-angled hexagons using the alternating side lengths. So here that's A, B, C, little a, little b, little c, or big A, big B, big C. So leave this as an exercise. Maybe a hint. Actually, you can take any hexagon and make it look like this picture by applying an isometry to your favorite side and putting it here. And then it's not so hard to see that this hexagon is determined by little a, big B, and big C. Okay, that's not so hard. And then you just need to see that big A is determined by little a. Okay, so that's one thing. So, okay, great. What do I do with right-angled hexagons? Well, if I have right-angled hexagons, if I take a right-angled hexagon and another copy of that same right-angled hexagon, I can glue them together to build a pair of pants. So I can glue 2 hexagons to build a pair of pants. Okay? So this is now, so here's one hexagon P, and here's another copy of it, upside down P. Okay, and they're glued together along these sides. So, so what is this? This is a hyperbolic surface with boundary. The boundary is a geodesic. That's why it was important for these angles to be right angles. And now if I take this and I double it over the boundary, I get a genus 2 surface. And that has a metric that's locally isometric to the hyperbolic plane. Okay? But more generally, we'll get to that in a second. So step two, another proposition, hyperbolic pants with geodesic boundary are determined up to isometry by the lengths of the boundary. Lengths of boundary. Okay, so why is that? Well, look, if I have a pair of pants that I build from a pair of hexagons, okay, I needed to know that the lengths of these sides of the hexagon were the same to glue them together. But notice that tells me that the lengths of these sides are also the same. Okay? So if I take any hyperbolic pair of pants, I can draw the topological arcs between boundary components like this, pull them tight to geodesics, prove that what I've done is decompose this into hexagons. Then I know that the lengths of these are the same, so the two hexagons are isometric. That tells me the lengths of these arcs are the same. But then these arcs this arc is half the length of this circle, and so these alternating arcs tell me the length of the pants. Okay? All right, so maybe that's quick, but that's an exercise. Step 2. Step 3, let's build some surfaces. Step 3, build surfaces. Let me start with any collection of pants. So glue hyperbolic pants. So here's a genus 2 or genus 3 surface. I obtained it by gluing together 4 pairs of pants. Let's fix your favorite lengths for these curves. And now I can build pants that have those lengths. And then I can glue them together to build a hyperbolic surface. Okay? Now there's some choices involved in gluing. Right? All I need to do is I need to make sure that when I glue this pair of pants to this one along this geodesic boundary, I need to make sure that it's glued by an isometry. There's a whole circle worth of isometries. Okay? So there's lots of flexibility in this construction. There are 3g minus 3 parameters. That's the number of curves that I need. And then there's 3g minus 3 more parameters, real parameters that tell me how to glue them together. So I can build lots and lots of hyperbolic surfaces this way. Okay, step 4, this is everything. So why is it everything? Take an arbitrary surface, arbitrary hyperbolic surface, X, let's say genus G, at least 2. Take a pants decomposition of curves. So I just mean a collection of curves that cut the surface up topologically into pants like that. Pants decomposition of X. So again, here's my surface. Let me try to, so whoa, it's wavy. It's not a geodesic. Whoa, wavy. OK, these are just curves, closed curves that cut the surface up into pants. Now apply this, straighten all of those curves to geodesics. OK? Little exercise. If we have gamma 1 through gamma 3g minus 3, these are my curves, then gamma 1 star through gamma 3g minus 3 star is also a pants decomposition. But now it's a pants decomposition with geodesic pants curves. Okay? And I obtain the surface by gluing together pants like in step 2, okay? So an arbitrary surface looks like one of the kind that I constructed. Okay, let's take 3 minutes. Stand up. It's gross. Okay, do you have any questions while we're, yeah?
How many decompositions did you have pants for?
Oh, that's a great question. So up to homeomorphism, yeah, you can try to count how many ways you can cut the surface up into pants like that. Somebody here must know estimates on this. I don't personally, but there are estimates, asymptotics on how many ways you can do it. I can't even remember the order of growth. Probably exponential or something. But yeah, there are lots of ways of doing it. So at this point, I'm not parameterizing any kind of structures. We'll get to some parameterization later. We'll talk about Teichmuller space. But now this is just, so yeah, there's a lot of dependence on the Pancy composition I picked. But it's just saying that every Riemann surface looks like one constructed in that way. Yeah.
So what happens for Riemann surface of genus 1?
Ah, okay. So for Riemann surface of genus 1, the universal cover is not the upper half plane. It's the complex plane. Then the covering group is acting by holomorphic automorphisms of the complex plane, which is the group of complex affine diffeomorphisms. And, well, if you have, so a complex affine diffeomorphism could be a similarity. But a similarity has a fixed point, and we know the action is free. It's a covering action. So there are no fixed points, which means that all of the isometries have, all of the covering transformations, these affine automorphisms, are actually isometries. Okay? Not only that, but we know that if we had an isometry that wasn't a pure translation, then we'd have to have a fixed point also, which means that we're actually acting by translations. So every genus 1 Riemann surface is the quotient of the complex plane by a group of Euclidean isometries acting by translation. And the Pants decomposition picture is the wrong one there. Instead, you could take a single curve. If you cut along so taking a single curve, you can straighten it to a geodesic, and with respect to the Euclidean metric, cut open, and now you get annulus. And so you can describe all Riemann surfaces of genus 1 as Euclidean annuli, where you glue the annuli in a sort of similar picture. Yeah?
And these surfaces are in particular algebraic curves. Is there a way to get an algebraic expression starting from this example?
I would ask someone else. Yeah, that's right. So every Riemann surface can be realized in various ways as an algebraic curve. So embedding into projective space, making an algebraic curve. I think I don't know anything more than what I just said. Someone else maybe, yeah. Oh, you're going to answer. No, you already raised your hand. You have to. Just kidding. Yeah. Yes. So, all right. So the geodesic is unique up to reparameterization. That's right. And in fact, really, when you prove this part 3, or actually, when you prove part 2, what you see that geodesic has to be the image of the axis of this hyperbolic isometry. So you can prove part 1 by just taking a sequence of representatives that are trying to minimize the length. That will have a limit. That's your geodesic. You can lift that to the universal cover. That will be a geodesic in the universal cover, and you're acting by translation on it. And so in the universal cover, the axis is unique. Okay, so let's see. We're just under an hour, I think, in. So we'll do another half an hour. I swear I won't go more than a half an hour. As a good friend of mine, Dick Canary, says, nothing I have to say can be more important than your lunch. So. Okay, so let's now switch gears and we're going to talk about Teichmuller space. Okay, so we talked about Riemann surfaces and how different ways of thinking about them. So now we're going to talk about Teichmuller space. Okay, so the setup is S is going to be a topological surface. So this is just a topological surface, genus G greater than or equal to 2. I should say oriented. And so let's draw a picture of it to slow me down. Okay, so surface S. And now I want to think about Riemann surface structures on S. Okay, now one way to think about that is just an atlas of charts on S to C so that the transition functions are holomorphic, like we've been talking about. Or we can think about it as a metric on S that induces the topology so that it's locally isometric to the hyperbolic plane, either one of those. But actually, I want to think about, it turns out that it's often easier here to think about this in a slightly different way. It's equivalent to that, but namely, I want to think about, a Riemann surface structure on S. So I want to think about it as a Riemann surface that S wears, like clothes. Okay? So we have Riemann surface clothes. So a Riemann surface structure on S is an orientation-preserving homeomorphism from S to a Riemann surface. So this is an orientation-preserving homeo to a Riemann surface X. So I can just pull back that atlas of charts. I get an atlas of charts on S that defines a Riemann surface structure. So same thing, but it's just more convenient. Okay, so that's what a Riemann surface structure is from now on our topological surface S. So Teichmuller space is the space of equivalence classes of Riemann surface structures. So let's be more precise. So let's give the definition of equivalence. So let's define F from Sx to be equivalent to H from S to Y. So these are two Riemann surface structures on S. So what does it mean to say that they're equivalent? Well, I want X and Y to be holomorphically diffeomorphic or isometric as hyperbolic surfaces. But I want that holomorphic map or that isometry to respect the way that S is wearing those Riemann surfaces. So we'll say that if there exists a holomorphic map or isometry sigma from X to Y such that if I do F and then sigma, that's homotopic to Y. To H. So let me draw it in a diagram. So I've got the map from S to X, and I've got the map from S to Y, and I've got a map here. And I don't require that this diagram commute. Instead, I require it commutes up to homotopy. That's a good symbol for that. Okay? So meaning if I go F and then sigma, that's the same as H up to homotopy. And now I should say that for surfaces, closed surfaces, two maps are homotopic if and only if they're isotopic. This is a classical fact for the topology of surfaces. And in some sense, I don't really care. Just think about homotopy, or if you know that they're the same, you can think about isotopy, or you can think about either one. It's up to you. It doesn't matter for most of what we're going to say. Okay, so that's, let's call the equivalence class of F from S to X is denoted just like this. Okay? So the equivalence class of this Riemann surface structure will be denoted like this. And are there questions about this definition? So basically, we're saying that the Riemann surfaces are the same. And the way that S is wearing those Riemann surfaces is basically he puts on one pair, and then, or he puts it on the same pair, but kind of a little bit twisted. Okay? Straighten it out, and it's the same. Okay, so what is Teichmuller space? As a set, So as a set, it's the set of equivalence classes. Riemann surface structure. It's just, so that's, the points in Teichmuller space are just equivalence classes of Riemann surface structures on S. All right. But as a set, I mean, a set is not very interesting by itself. We want some additional structure. So we're going to talk about some structure that we can put on Teichmuller space. Let's start with the metric. Okay, this is, let's talk about the metric on Teichmuller space, and in particular then in topology. To talk about the metric, we need some more technology. We need to talk about quasi-conformal maps. So quasi-conformal maps. OK, so let me just start by saying that whatever this metric is, it's going to measure how different the Riemann surface structures are. Okay, so we need some way of measuring how different Riemann surface structures are. So let's start with we're going to measure that using quasi-conformal maps. So let's start with definitions. And let's start with the easy case. In fact, I'm basically just going to do the easy case. So let's say U and V are open sets in C. A map, F from U to V, orientation preserving, let's say, diffeomorphism. We'll say that this is K quasi-conformal if, well, I want to say that the map doesn't distort the complex structure on C very much. Okay, or by at most K. So I need some measurement of that. So let me write down two things. So one, we take Z inside of U. So the derivative of F at Z. So this maps the tangent plane to U at Z to the tangent plane at F of Z to V. Okay, so it's a map from R2 to R2. And if this was, so I want to think of the tangent space as a copy of R2, okay? And the reason is that F is not holomorphic, so the derivative isn't a complex linear map. It's just a real linear map, okay? So the derivative is the tangent space at Z to U to the tangent space at F of Z to V. And what does it do to a circle? Circle, well, if it were actually differentiable, complex differentiable at Z, then it would send this circle to a circle. But it's only real differentiable. So it sends the circle to an ellipse. Sends the circle to an ellipse. And what I want, a measurement here of how far it is from being conformal is how far is that ellipse from being a circle. And that I can measure as the ratio of the length of the major axis to the minor axis. So for all Z, K, let me say the ratio of the major axis over the minor axis should be less than or equal to K. Okay, and I'm not writing everything. Is it clear what I mean? Okay. So another way to write the same thing, notice that if the derivative df at Z, if this were actually area preserving, then the ratio of major to minor axis, the major axis times the minor axis length would be 1. Okay? So, sorry, major radius to minor radius is 1. So, okay, so what I can say instead is that equivalently, so we can look at the derivative of F. We can take the norm of the derivative. So the norm of this is a linear transformation. We have a norm on the domain. We have a norm on the range. The norm of the transformation is just you take the soup over all unit vectors in the domain and take the norm of the image. So if the norm over the determinant, so the Jacobian, is less than or equal to K. Okay? So I'll leave it as an exercise to prove that this is equivalent to that. It's not so hard. This is a useful formula. Dividing by the determinant is essentially treating it as an area-preserving map. And then in that case, we're just saying the norm of the derivative squared is at most k. This is the operator norm. So norm df z is equal to the sup over all v not 0 df z over. Okay. All right. So this is what it means for a map to be k quasi-conformal. The infemal k, we'll define that to be k sub f. So it could be, if it's k quasi-conformal, then it's also k plus 1 quasi-conformal, k plus epsilon, right? So we can try to take the infemal k, for which it's k quasi-conformal, and we'll denote that by k sub f. So this is sort of the worst. The complex structure is distorted by the map f. Okay? So maybe something to note about this, a remark, if I pre-post-compose with a holomorphic map, a conformal map, then it's also k quasi-conformal. Okay? That's an easy exercise. Pre and post composing, that's just dilating and rotating. Okay, so it's not going to change sort of how much things are stretched. Okay. So this is one way that you can measure the distortion of complex structure. It's the optimal f of a quasi-conformal map. Okay? So an alternate picture that's also useful. So we can differentiate our, so we can think about z and z bar as variables, and we can differentiate with respect to z and z bar. This is derivative with respect to z. That means, this is 1/2 derivative of f with respect to x minus I derivative of f with respect to y. And we also have f z bar. So 1/2 derivative of f with respect to x plus I derivative of f with respect to y. So another way you might measure the failure of a map being conformal is you can measure the failure of the Cauchy-Riemann equations being satisfied. And notice that what I wrote down there, so a little exercise is, oh, I'm supposed to move up and start. Okay, exercise. F z bar equals 0 is the Cauchy-Riemann equations. So a map is conformal if f z bar is 0. Okay? And then you can use f z bar to measure how far you are from being conformal. But that's not very good if you sort of scale things. So instead, yeah. Oh, sorry. Yeah, okay. This one's minus. This one's plus. So if this is satisfied and if satisfied, then f is holomorphic, and the derivative is the derivative with respect to z. Okay. All right. Now, if I scale things, both of these quantities scale. So the right thing to do is divide by the two. So if I write, let me write mu sub f as f z bar over f z. Okay, and this gives me another measurement of how far the map is from being conformal. Okay, so it turns out that this is less than 1 everywhere. In fact, we're on a compact Riemann surface, so this is, well, no, we're still on, yeah, we're still looking at maps between open sets and C. Okay, so this is, if the sup of this is less than 1, then we get a map that's quasi-conformal. And in fact, f is k quasi-conformal if and only if 1 plus mu f over 1 minus mu f is less than or equal to k. So in fact, this quantity, also write as fz plus fz bar over fz minus fz bar. So this quantity, this less than or equal to k, is equivalent to this here. So let's call this maybe star. So this is equivalent to star. So really, they're not different ways of measuring how far you are from being conformal. Okay, they're related by this formula. So two different ways of thinking about the same way of measuring how things are different from being conformal. Let me come back to this. Pre and post composing with holomorphic maps preserves whether a map is k quasi-conformal, which means that we can make sense of k quasi-conformal maps on a Riemann surface. You just look at any holomorphic coordinates, and this says that it's independent of which coordinate we chose. So if we have a map which in local coordinates is k quasi-conformal in one set of coordinates, and it's also k quasi-conformal in any other set of coordinates. Okay? So far, this has all been about diffeomorphisms that are k quasi-conformal. So now let's say a definition. So maybe, f from x to y, an orientation preserving diffeomorphism is k quasi-conformal if it is in local coordinates. Okay? So that remark tells you that it makes sense. And then let's now say, so here x and y Riemann surfaces. And let's say that a k quasi-conformal map, so f from x to y, an orientation preserving homeomorphism is k quasi-conformal if it is a limit. So in the compact open topology of k quasi-conformal maps. So if you don't like this, that's OK. Just of k quasi-conformal diffeos. The point is that the quasi-conformal maps that we're ultimately going to look at, Teichmüller maps, are they're not diffeomorphisms. In that case, there's a finite number of singularities where it's so a finite number of points where it's not differentiable. So you could use that, but it's sort of artificial. OK, so this is what it means for an orientation preserving homeomorphism being quasi-conformal. In fact, you can talk about partial derivatives with respect to z and z bar. They're locally integrable functions that are weak derivatives. You can ignore that if you want and just pretend that everything's a diffeomorphism. Okay? There's really not much.
Can you say what is he looking at this?
Yeah, this is in the compact open topology.
What would be an example of something?
So I'll give an example in a little bit. Yeah. You could. So maybe one example is you could take just a map. Maybe yeah. So here's an example. Take x plus iy goes to x plus so say k x plus iy. So a quasi-conformal map is a diffeomorphism. But then I could compose with let's say z goes to z squared. So that's a map from, and then I want to, no, that doesn't. The natural examples will come up later. Yeah.
Sorry, can you obtain every quasi-conformal as a limit of?
As a limit of diffeomorphism, yes, yeah. Yeah, that's the definition I gave, yeah.
Okay.
Yeah, that's the definition I gave. But I mean, there are other definitions, maybe more direct definitions that don't come from limits. Sorry, this is not, yeah. We're getting close to lunchtime. I will give another example, though, hopefully. OK. Right. OK, we're about ready to define the metric, but we need some facts. So facts about quasi-conformal maps. First one's an exercise proposition. K quasi-conformal. Let's suppose we have f from x to y, h from y to z, where f and h. So f is k quasi-conformal, and h is k prime quasi-conformal. Then f inverse is also k quasi-conformal. So inverses of quasi-conformal maps are quasi-conformal. If you think about the picture, that's obvious. That's true for diffeomorphisms. It's fairly straightforward, and then you can take limits and check that this is true. The other thing is that if I compose, so fh is k prime quasi-conformal. And I think that derivative norm definition maybe is a good way to see that. Okay? Okay, so that's one fact. So proof exercise. Right, theorem. K quasi-conformal maps from x to y are compact in the compact open topology. So I look at all k quasi-conformal maps from x to y. I have a sequence of such things. And the limit is, again, a k quasi-conformal map. Okay? The limit, so up to subsequence, there is a limit, and that limit is k quasi-conformal. Okay? And again, this is in the compact open topology, or if you like, topology of uniform convergence. Okay, these are compact sets. Okay, so that's nice. And then the last thing, this is sometimes called the Weil's lemma. And it says that a one quasi-conformal map is conformal. And well, for diffeomorphisms, that's obvious, right? The limits of diffeomorphisms, it's maybe not so obvious, right? This is something about differentiability almost everywhere. This one, k quasi-conformal maps from x to y. So the set of all k quasi-conformal maps are compact. So in the compact open topology on maps. So all continuous functions from x to y. It's just saying that you have any sequence of k quasi-conformal maps, so there's a subsequence that has a limit, a uniform limit, that's k quasi-conformal. Okay. It's okay?
So here maps, you mean homeomorphic?
Here maps, I mean, yeah, so from now on, k quasi-conformal always means k quasi-conformal homeomorphisms. So it turns out you can treat them just like diffeomorphisms. Formally, everything is fine. It just requires some more technology. Okay. All right, let's define the Teichmuller metric. So call it d sub t. It's a metric on Teichmuller space. So what is the distance between these two equivalence classes of Riemann surface structures on S? Okay, I've got two different equivalence classes of Riemann surface structures. I want to measure how different those are. Okay? So I'm going to define it to be the inf. I'll write down what it is an inf of in a second. Inf of 1/2 log k capital F. And the inf is over all maps F from x to y that are quasi-conformal. Okay? So this is, remember, the optimal quasi-conformal constant. So that are quasi-conformal and homotopic to the right thing. Okay? So the right thing here is F inverse H. So let's draw the diagram again. Okay, here's S, here's X, here's Y, here's F, here's H. We want a quasi-conformal map that makes this diagram commute up to homotopy. Okay? So we have a preferred homotopy class of maps here. And we're saying let's take the optimal quasi-conformal constant for all maps. Okay? And then to get a metric, we take log. The 1/2 is because if you stretch by k and contract by 1/k, that's k squared quasi-conformal. So the square, anyway. All right. So this is a function we just defined. It measures how far this map, this homotopy class of maps, is from being conformal. Okay? So it measures the right thing from the perspective of what I suggested earlier we are trying to measure, how far things are from being conformal. Okay, so yeah. So for diffeomorphisms, it's obvious. So you could have something which is a limit of kn quasi-conformal maps where kn goes to 1. They're diffeomorphisms, and the limit will be 1 quasi-conformal, but yeah.
But I saw the definition of k quasi-conformal
You're right. So k quasi-conformal, I just erased it. So the definition of k quasi-conformal is a limit of k quasi-conformal diffeomorphisms. And then k sub f is the infimum. I wrote it in the wrong order. K sub f is the infimum of k so that the map is k quasi-conformal. So you could have a map, a homeomorphism, which is a limit of kn diffeomorphism. So 1 plus 1/n quasi-conformal diffeos. So f sub n from x to y. You could take a limit of these. So f could be the limit of the f sub n's. And f isn't necessarily a diffeomorphism. But it's kn, it's 1 plus 1/n quasi-conformal for all n. And then because we're taking the infimum of such things, it's actually 1 quasi-conformal. Does that clarify? Yeah.
Such a map exists.
Yes. Any diffeomorphism will be, because x and y are compact. So remember, x, we're thinking about the Teichmüller space of a closed surface. The norm of the derivative is continuous, so it's bounded. Yeah. So there is such a map. And now we're going to prove that this actually defines a metric using these facts. Yeah.
So I'm sorry.
Mm-hmm.
Sorry for that.
No.
No, I don't understand this statement anymore.
Which one? This one?
It's conformal, but not a diffeomorphism?
It's 1 quasi-conformal.
Yes.
So for example, it's a limit of.
The conclusion is conformal.
The conclusion is it's conformal, and hence it is a diffeomorphism. Yeah.
So what?
So the assumption is not that it's a yeah.
So in this case, the conclusion is it is a diffeomorphism.
That's right. So it's not obvious here that the limit should be a diffeomorphism. It's just a uniform limit of diffeomorphisms. So it doesn't have to be a diffeomorphism. But the conclusion of Weil's lemma is that in fact it is a diffeomorphism and it's conformal. Yeah. Okay. Any other questions? Dangerously close to making you late for lunch. So let me let's say y is dt a metric, and then if you want to see an example, well, okay, dt is a metric. So why is it a metric? So first of all, this and this tell us that it's symmetric and satisfies the triangle inequality. So the proposition implies that it's symmetric and satisfies the triangle inequality. Okay? The fact that k is the ratio of major to minor axis is bigger than or equal to 1 says that it's positive, so non-negative. Non-negative. Since a k quasi-conformal map, k is always greater than or equal to 1. Okay? So it's symmetric, triangle inequality, it's non-negative. So the only thing we need to see is that it's non-zero on distinct points. And that's where these two things come in. Okay? So why is it non-zero on distinct points? If I have a sequence of points where, sorry, if I have a pair of points where this infimum is 0, that means I actually have, I can take a sequence of quasi-conformal maps. Okay? By this theorem, I can take a limit of those and get something that's quasi-conformal. And in fact, it's one quasi-conformal. And then by Weil's lemma, it's conformal, which means that they're equivalent. Okay? Does that make sense? All right. So we have 1 minute. Let me give you really quick an example of a non-diffeomorphism. So here's and this is a good example for next time for Teichmüller GDS. Here's an example of a surface. So I'm going to build a Riemann surface by gluing together this rectangle in the way that I'm describing here. Okay, and then, so the top is cut up into 4 segments, the bottom into 4 segments, let's say equal length. I glue them together and I get a genus 2 surface. Okay? And now let me look at the map. I can do the same thing, but with a different shape rectangle. So, and I have the affine map between here and here. X plus iy goes to, let's say, kx plus 1 over k iy. Okay? This gives me another genus 2 surface. This gluing is by translations and possibly rotations through 180 degrees. I get a complex structure out of this. It requires a little thought. Same here. I have this map, which is a diffeomorphism away from these points. Okay, these points are actually, at these points, this map between these two genus 2 Riemann surfaces is not smooth. Okay, lunchtime.